Welcome to the massive open online course on Aspen Plus. In this week, we are discussing about the process and property analysis. In today's lecture, I'm going to discuss about the modeling part, ideal model, equation of state models, activity coefficient, and the special models. We will also discuss the pure and binary ternary parameters and how to plot the relevant data. This portion will be covered today. First, let us understand what is property method. Already we have discussed the property method in a nutshell while we simulated some of the processes in the first 3 weeks of our lecture series, but we'll learn in detail over here. Now, the property method is a collection of models and methods used for calculating the physical properties of component, namely the thermodynamic and transport properties. What are the transport properties? We have three types of transport properties related to mass, heat, and momentum. For mass, we have diffusion coefficients. For heat, thermal conductivity, convective heat transfer coefficients. And for momentum, we have surface tension, viscosity, etc. And what are the thermodynamic properties that we have? Mainly physical and phase equilibrium properties. In physical properties, we have density, molecular weight, enthalpy, entropy, Gibbs free energy. And for phase equilibrium, we have fugacity coefficient, chemical potential, K value, etc. And these properties are calculated through K method. Equation of state, that is ideal gas law, real gas law such as Peng-Robinson and Rayleigh-Quangs-Wave, that is for vapor phase. And for liquid phase, that is real solution, we have Raoult's law, Henry's law, or activity coefficient method for liquid-liquid interaction, fugacity, NRTL. When we do not have the molecular interaction in the liquid or vapor phase, we can use ideal gas or ideal solution laws. But the moment we have liquid-liquid interaction, the molecular interaction between two liquid elements or two gaseous elements, in that case, it will be real gas law or real solution. For that, we have to use activity coefficient method for real solution or real gas law, equation of state. Now, we also have some special systems such as steam, which is exclusively for water and steam. And for amine model, amine package, we have amine package for various amine products. Grayson method, mainly for petrochemical systems and for solids. We'll learn them one by one. Next, we will learn about method versus model. Now, many a times we use the word method and model interchangeably. Sometimes we say method, sometimes we say model, but there is a slight difference between them. Method is actually a set of models which are used for calculating or computing the process parameters or physical property parameters. And model is a set of mathematical equations in order to obtain that required properties. So model may have only a single equation or it will have multiple equations. And method may contain only one model or it can be a set of models working together. Okay. So among the set of models, we have three types of models: thermodynamic model, transport model, and non-conventional models. So as we have already discussed before, that model is basically a set of mathematical equations, mathematical models. So those mathematical models are there for these items. In thermodynamic case, we have equation of state, activity, vapor pressure, liquid fugacity, heat of vaporization, molar volume, density, heat capacity, solubility correlation, and other thermodynamic properties. Whereas in transport models, we have viscosity, thermal conductivity, diffusivity, surface tension, etc. And there are certain non-conventional models which will calculate general enthalpy and density, or say enthalpy and density model for charcoal. These are special models that we have. Aspen Plus has property methods which contain these thermodynamic models which are very commonly used. Okay? And users can modify the existing property method which are available in Aspen Plus database, or they can create absolutely new customized property methods if the need arises. We will discuss them after a few slides. Now, the choice of appropriate property method is definitely the prime issue in determining the accuracy of one's simulation results. As I said, that there can be various combinations of vapor phase and liquid phase. It may be ideal gas, ideal solution, ideal liquid solution or ideal gas, this combination. That means when there is no intermolecular interaction, in that case, we can use ideal model property method. But the moment there is some interaction between two liquids, especially for, say, real solution, that means when some polar components are present in the solution, then definitely there will be some liquid-liquid interaction. In that case, it will no longer be an ideal solution, it will be a real solution. But the gas phase may be ideal. In such situation, we have to use activity coefficient based model. On the other hand, if there is no intermolecular interaction in the liquid phase, that means the liquid phase is ideal, whereas there are intermolecular interaction in gas phase, that is real gas. It is no longer the ideal gas. In such situation, we will use equation of state based model. There you will have real gas interaction and non-polar liquid. If the liquid has non-polar components, then there will be no interaction among the liquid-liquid molecules. But the moment polar components come in the liquid, we will have some interaction. And the fourth combination may be real gas and real solution, where there will be liquid-liquid as well as real gas interaction. In such situation, we will use some predictive kind of model. Now let us understand what is ideal system behavior. Now, as I said, that ideal system behavior means there will be no liquid-liquid or vapor-vapor interaction. There will be no molecular interaction between them. In such situation, say ideal gas, it will follow the ideal gas law, that is PV is equal to nRT. There will be small deviation, it is allowed, but large deviation is not allowed from PV is equal to nRT. And this will be valid only in the low pressure region and high temperature region. Similarly, in the liquid case, the ideal solution should be very dilute solution, and it will follow the Raoult's law and Henry's law. Now, already yesterday we have discussed what is Henry's law. We know that for very dilute solution, if the mole fraction of a component in the vapor phase is Y, and the mole fraction of the same component in liquid phase is X, then for a dilute solution, Y by X is constant, and this constant is called the Henry's constant. This is the Henry's law. Whichever the component that follows this law is called Henry's component. And we have given certain examples like CO2 in water, it follows Henry's law. And Raoult's law, as you know, that the dilute solution, this condition is not required. For Raoult's law, it is the entire concentration range between two components will be valid, and it is between nonpolar components for similar size and shape. For instance, if it is benzene plus toluene, or say pentane and hexane, they follow the ideal solution behavior. In such cases, they will follow Raoult's law. That means for the entire range of this concentration, even for 50% benzene and 50% toluene case, when the solution is not dilute, even for this case, this kind of logic or this kind of relationship holds. In such situation, the partial pressure of the component in question, if we are discussing about benzene toluene system, then say partial pressure of benzene in the vapor phase by the mole fraction of benzene in the liquid phase, that ratio is equal to the vapor pressure of benzene, okay, for that particular temperature. Obviously, this relationship will change with temperature. So this is called the Raoult's law, and ideal solution follows Raoult's law, and they will have negligible intermolecular interaction. Ideal activity coefficient model for the liquid phase, we will have activity coefficient to be 1. And it can be identified with the property analysis plot, that is temperature versus the mole fraction xy, or pressure versus mole fraction xy, or xy, that is the vapor liquid equilibrium diagram. So ideal system behavior can be identified with all of them. Now we come to the next section. This is an example, that is vapor liquid equilibrium of benzene toluene binary system that we were discussing a few minutes back. Now this vapor liquid equilibrium for benzene toluene binary system has been taken from this particular journal. It is Chinese Journal of Chemical Engineering, volume 1, published in 1993. They demonstrated some experimental study, and the result that I have tabulated over here, that is obtained from this particular journal paper. And I have plotted this over here. So you can see you will have some kind of plot. Okay, now let us see whether benzene toluene binary system follows ideal behavior. For that, we have to go to the Aspen Plus simulation window. Let us go to Aspen Plus simulation window, and so benzene and toluene are added. Press next, and we'll use ideal method. So let us run. Yes. Now you can observe over here analysis, this binary analysis. So here you can generate TXY, PXY gives free energy mixing curves for binary system. So we will try to find out the vapor-liquid equilibrium for benzene-toluene binary system. So let us click over here. So this is the analysis type, TXY, benzene-toluene. Basis is mole fraction for benzene. And we have starting point 0, ending point 1, that is the mole fraction 0 to 1 for benzene. And we have number of intervals 50. And the pressure is 1 atmosphere. So let us run analysis. So this is the TXY diagram for benzene-toluene system at 1 atmosphere. Okay. So at different temperature, the values of X and Y will differ. So this is the X diagram and this is the Y diagram. So this is the bubble point and this is the dew point. Bubble point curve and dew point curve. Now go to the plot and plot YX, because this is the vapor-liquid equilibrium curve. And check, this is the vapor-liquid equilibrium curve for benzene-toluene system using ideal model or ideal system behavior. Now let us compare it with this one. So this is the experimental result and this is the model result. Let us see how close they are. And this is the closeness, this is the actual, and this is the ideal behavior. Okay. So you can understand that the experimental result and the ideal model behavior, they almost superimpose on each other. So we can say that benzene-toluene binary system, it demonstrates ideal behavior. Okay. But is it true for water-phenol binary system? Let us try. We have got the data from this particular journal paper, Journal of Chemical Engineering of Japan. They have published some paper and I have taken the data from there. And this is the XY data and I have plotted over here. Okay. This is the experimental data. Now let us try to see whether the ideal model behavior works for it. For that, let us go back to component, water and phenol. So write water and phenol. Now the model is there, run. Okay. Now again you take this binary over here. The second binary unit comes up. Press water and then phenol. Mole fraction of water from 0 to 1 with 50 intervals. Pressure remains same. Run analysis. Okay. Again, you can find this is the bubble point curve and this is the dew point curve. Now bring in the YX diagram. Yes. So you have got the YX diagram for water and phenol system at 1 atmosphere pressure. Now can you compare this with this? Yes, we have done. And this is the comparison. This is the actual curve, the red triangle, and the ideal curve is the blue circles. Surely they do not match with each other. Now we have tried Wilson also. Wilson is another activity coefficient model. That also we have tried, and that also do not match with the experimental data curve. So we have to find some other property method for water phenol binary system, but definitely it is not an ideal behavior. So it's a non-ideal solution. We can certainly say that water phenol binary system is a non-ideal binary system. Definitely because water is a polar compound. It's not non-polar. So because it's a polar compound, there will be some intermolecular interaction. Now here we have got some activity coefficient based model. They are Margulies, Vandler, Wilson, NRTL, and Uniquark. Now the binary parameters of NRTL and Uniquark, they have been regressed using vapor-liquid equilibrium or liquid-liquid equilibrium data from the Dortmund data bank. Now we see that for binary systems, multi-component systems, agiotropic systems, and liquid-liquid equilibrium, for 4 of them, almost all the activity coefficient based model, they work, except Wilson model doesn't work for liquid-liquid equilibria, and Margulies and Vandler model, they have limited applicability on multi-component system. But this Margulies and Vandler model, they do not work for dilute system and self-associating system such as sedimentation and electrolyte. But Wilson, NRTL, and Uniquark, they work for this kind of system. The polymer systems, only Uniquark model works. None of these Margulies, Vandler, Wilson, NRTL, they work for polymer system. And for extrapolation kind of work, we cannot use Margulies and Vandler. We have to use Wilson, NRTL, or Uniquark activity-based coefficient model. Now we have certain recommendations for mainly binary systems. The last one will be for multi-component mixture. Here, for binary system, we have 2 components. If both of them are non-polar, then all the models will yield reliable data. But if one of them is non-polar and other one is weakly polar, then all the models are good. However, Uniquark model is better than others. And if there is a non-polar, strongly polar combination, in such situation, all the models are good. However, Wilson model is the best for such non-ideal system. And when we have a combination such as weakly polar or weakly polar, strongly polar, and strongly polar, for this kind of system, Uniquark model is better than others. Again, for aqueous solution of strongly polar component, that means one of the component is water, the other component is strongly polar component, then Uniquark model is the best. And aqueous solution of weakly polar or non-polar components, none of these model work due to poor or limited solubility. Because water is a polar solvent, and if the component is non-polar or weakly polar, then it will not be dissolved in water. So none of these models work. Solutions with carboxylic acid, Wilson model is the best. if the components are mutually soluble. Otherwise, Uniquark, Van Laer or inertial model should be used. If the solutions contain polymers, then you have to use Florey-Huggins model. If the solutions contain strong acid or bases or ionizable salt, then you have to use Debye-Huckel model. So these are for binary systems. And for multi-component mixtures, the model has to be chosen based on the dominant component in this mix. So suppose we have a combination of A plus B plus C, then we have to see what are the dominant component in this mixture, whether it is A and B or B and C, or it is A and C. So the dominant components will decide what should be the binary system, and you have to plan your property method. Now we have heard of UNIFAC model, but we have never used it till now. The question is, what is UNIFAC model? UNIFAC model means it's a short form of Uniquark functional group activity coefficient. This FAC. So UNI-FAC. It is UNIFAC model that way. So that has been developed by Frerensland and Jones and Prausniks in 1975. It has been published in AICHE journal. So interested people can go and refer this particular journal paper to understand more of UNIFAC model. It is semi-empirical model to predict the non-electrolyte activity in non-ideal mixture. It uses the functional groups in ideal solution to calculate the activity coefficient, and it is a group contribution model, hence it is predictive in nature. So in many combinations, the direct interaction is not available. In such situation, UNIFAC model predicts the interaction beautifully. So it's a good approximation method for missing pairwise interaction parameters. And it uses the property constant estimation PCES regression that provides Bondi method, which requires only the molecular structure as input. And if more accuracy is needed, then you have to use experimental data rather than the UNIFAC model. We shall learn it better by using an example. So this is the example. It says, comparative study of flashing equimolar mixture of water, hexane, phenol and benzene at 105 degrees centigrade and atmospheric pressure for the models ideal, Van Laer, Wilson, inertial, Uniquark, and use UNIFAC to find the missing parameters. So let us see what it does. Now this particular example does two things. One is it shows how the choice of different property method yields different result. That is the number one. And number two lesson that we find is use of UNIFAC method to find missing parameter. Okay. Now let us go to the Aspen Plus example. Now in the components, we have to have water, hexane, phenol and benzene. So water, phenol and benzene is there. We have to use hexane. And we'll use first ideal model. So ideal model is already there. What are the models we have? Van Laer, Wilson, inertial, Uniquark. So Van Laer, Wilson, uniquark, and inertial. Okay, so press next. So this is done. Next is inertial. This is also done. Then uniquark. This is done, and finally Wilson. Yes. Now for the time being, let us use ideal method. Okay. Okay, property methods are fixed. Now we have to go to the simulation chamber. So go to Flash, bring in Flash over here, materials. So this is feed, this is vapor, and this is liquid. So just rename them. It is feed, this is vapor, and this is liquid. Press next. We have 105 degrees centigrade and atmospheric pressure, so 105 and atmospheric pressure, and we have equimolar mixture of water, hexane, phenol, benzene. So equimolar of 4 things. So we say it is 25, should be 25, 25, 25, and 25. There won't be any toluene, and total it will be 100 mole, and it will be equimolar. All of them have same number of moles. Press next. We have to give the flash option. Let us say heat duty is 0 and the flash pressure, again it is 1 atmosphere. Now all the block parameters are set. Run it. Yes. Now the stream results are available. See what is the stream result. The molar flow, feed is 100, vapor 50.808, and liquid 49.1972. So vapor is 50.8028. 50.8028 and liquid 49.1972. 49.1972. Now let us run this with Van Laer model. So for that, we can go to the block option. We do not have to go back to properties. Here only we can change the block option from ideal to Van Laer. Yes, so we have got the stream results. So the molar flow rate, vapor is 48.0805. 48.08. So this is using Van Laer. Okay. Liquid is 51.91. 51.91. So using Van-Laar, it has reduced from 50 to 48. Now if you use Uniquark, then you are expected to have 74. Just check. Go to block option and go to Uniquark and run. See the stream result again. It is 74.4484. 74.4484. So you can understand how by changing the property method, our simulation results change. That is why it is very, very important to choose a proper property method so that the results simulate the experimental data as close as possible. Okay? Otherwise, it will give a wrong result altogether if we do not use the proper property method. Now, the second task, we have to use UniFact to find missing parameters. So, what are the missing parameters? You go back to property method and see the binary interaction between all the components. For instance, go to Wilson method. Now, here we have the temperature dependent binary parameter with water and phenol combination. But do we have water hexane combination? We don't. Do we have water toluene combination? No, we don't. Water benzene combination? We don't have. So we have water phenol combination only. So other temperature dependent binary parameters in Wilson method we do not have at all. But we have the option to estimate the missing parameter by ticking this one, estimate missing binary parameters using UniFact or other methods. So just tick it and then run. The moment you run, all the missing parameters will come. See, water phenol was the last one. So we got water benzene, water toluene, water hexane, and phenol hexane was also absent. It was not there, but phenol hexane has been calculated. So all of them have been calculated using RPCES. Okay, RPCES that we have got from here. The regression using PCES. Now we will learn equation of state-based models for vapor mixtures. We have three typical models: Peng-Robinson, Redlich-Kwong-Swayam, and Lee-Kessler-Pöckler. These models. Now we have certain recommendations. If we have low pressure with no associating components, then we can safely use ideal gas mixture. But if we have low pressure with some associating components, then we have to use virial equation with only second virial coefficient retained. What is the virial equation? For ideal gas law, we know it is PV is equal to nRT, and virial equation is nRT into A plus B into rho plus C into rho square plus and so on. And this one, rho is equal to molar density. Okay. Actually, this is nothing but the compressibility factor J. And here it is said that only second virial coefficient retained. So all of them will be cut only this much is written. So actually it should be PV is equal to nRT into A plus B rho. So this kind of Fourier equation can be used for this system. And if you have slightly elevated pressure, then you can easily associate with either low pressure with associating components or low pressure containing associate component. So you can choose the cases as it may be. And if you have elevated pressure, then you have two choices. For vapor mixture containing hydrocarbons, inorganic gases, but not hydrogen fluoride, then you can use Peng-Robinson or Redlich-Kwong-Swayam model with van der Waals one fluid mixing rule. But if you have vapor mixture containing one or more polar or associating components, then you have to use Peng-Robinson or Redlich-Kwong-Swayam model with excess Gibbs energy based mixing rule and the appropriate activity coefficient based model. Now this is another example of similar nature that we had done a few minutes back. The same kind of example is given. So comparative study of flashing equimolar mixture of C1 to C5, that is methane, ethane, propane, butane and pentane. So instead of water, hexane, phenol, benzene, we are using C1 to C5 at 120 degrees centigrade and 50 atmosphere pressure for the models ideal, LKP, SRK and PR. That is ideal model, Lee-Kessler-Pöckler model, Redlich-Kwong-Swayam model and Peng-Robinson model. And this will be equimolar mixture. So earlier for this case, we took 25 moles of water, 25 hexane, 25 phenol and 25 benzene because we had 4 components. In this case, we are having 5 components, so we have to take 20-20 each. So the same thing we have to do and check whether we get these figures for vapor and liquid. So I won't do it here on the Aspen domain. I give it as a task for you to practice. Now Aspen Plus has some special system packages also. They are mostly amine property package for amine system. That means the system where we have lot of different kind of amines. If they are in the system, we can use amine package. And amine systems are popularly used for carbon dioxide sequestration. For electrolytes, we have a special version of NRTL method that is called eNRTL or ELEC NRTL package, and that is with Redlich-Kwong model equation of state. We have Grayson property package for petrochemical products, and for steam and water we have steam table, steam NBS, and more recently and more popular it is IAPWS 95 package, that is exclusively for steam and water. And there are some more property methods for gas processing unit. We have several applications and the corresponding recommended property methods. So we have hydrocarbon separation such as demethanizer or C3 splitter. For that we can use PRBM, that is Peng-Robinson Boston-Mathias property method, or Swayam-Redlich-Kwong Boston-Mathias property method. The same kind of property methods can be used for cryogenic gas processing, for air separation, If you have gas hydration with glycol application, then you can use Peng-Robinson-Wong-Sandler method or Swayam-Redlich-Kwong-Wong-Sandler method. You can also use Peng-Robinson MHV2, where MHV2 property package is used along with Peng-Robinson method. For acid gas absorption with methanol or NMP, we can again use Peng-Robinson-Wong-Sandler or SRK-Wong-Sandler. For acid gas absorption with water, ammonia or amines, you can safely use NRTL method, NRTL rather. And for Claus process, you can again use Peng-Robinson-Wong-Sandler or SRK-Wong-Sandler method. To continue with the suggestions and recommendations, we have the property method suggestion for petrochemical unit. Several applications are suggested, like for ethylene plant, primary fractionator, we can use Chow-C and Grayson package. Chow-C means Chow-Cedar fugacity model. If we have ethylene plant with light hydrocarbons and separation train, quench tower, then we can use Peng-Robinson or Redlich-Kwong model. For aromatics, benzene, toluene, xylene extraction, we can use Wilson NRTL Uniquark model. For substituted hydrocarbons like VCM plant, acrylonitrile plant, we can again use Peng-Robinson and SRK. For ether production like methyl tert butyl ether or ETBE or TEM, we can use Wilson NRTL Uniquark. The same models can be used for terephthalic acid. And for ethyl benzene and styrene plants, you can use Peng-Robinson and Redlich-Kwong method. And for property method for chemical plants, we have recommended property methods like Wilson NRTL Uniquark for azeotropic separation like alcohol separation, phenol plant, liquid phase reactions like esterification. And if you have carboxylic acid for acetic acid plant, we have to use Hayden-O'Connell equation of state method to add with Wilson NRTL or Uniquark. For ammonial plant, you can use Peng-Robinson or SRK method. For fluorochemicals, you can use Wilson and HF. Ethylene plant, primary fractionator, again, you can use Chow-C and Grayson. Inorganic chemicals like caustic acid, phosphoric acid, sulfuric acid, HNO3, HCl, you can use ELEC NRTL. And hydrofluoric acid, you can use ENRTL HF package. So we end our lecture at this point today. Thank you.